Next slide, please. So before we get started, let's just address some logistics. For those who are attending the live webinar, we will take the Q&A at the end of the webinar. So make sure you select all panelists as well as attendees so everyone can see your questions and answers as well. And if you're watching this recording, feel free to ask questions on our Discuss forum at discuss.elastic.co, and make sure you tag your questions with the machine learning tag so your questions will be routed to the right team. And this recording will be available after the webinar on the SLED event page. All right, let's get started. So obviously, Elastic is known as a service, and some folks still refer to it as ELK stack. And as I mentioned earlier, the customers have been using Stack for years, and now we have just invested a significant engineering efforts into further developing the solutions, make them more enterprise ready, make them easier to use, and give you a better UI, and make ingest easier. And they are best in class across different markets. And because these solutions are built on one stack, any changes or new features we innovate in the stack, there will be immediate benefits reflected in the solutions as well. Next slide. From the deployment perspective, we provide a variety of deployment methods to meet our customers' needs, whether it's Elastic Cloud Enterprise, Elastic Cloud on Kubernetes, or self-managed deployment on-premise. Now you have the confidence that you can simply plug in and play in a secure, balanced mode without creating any technical debt with any extra infrastructure to fit the stack into the environment. All right, so today we will talk about machine learning. It is actually one of the components that's really tightly integrated with the Elastic stack. So we reap the benefits of machine learning in all three solutions. And today we'll specifically focus on how machine learning helps with the security solution. I'm going to hand it over to Tom and discuss in details.
Thanks, Jenny. So yeah, I'm the product manager for the machine learning team here at Elastic. Really happy to be talking to you all. And you know, one of the fundamental features of the Elastic Stack is having, you know, machine learning capabilities built in. And what we really focus on in the machine learning capabilities is to operationalize and simplify kind of data science techniques. And, you know, what does that mean? You know, when we're building the machine learning features, it's all API first. You know, you're able, just like the rest of Elasticsearch, it's built into the core of Elasticsearch and Kibana. Simple workflows, ways to use that all the way through kind of our solutions and, you know, through the different workflows within Kibana. When I talk about machine learning today, I'll specifically be talking about two different pieces. One is called time series anomaly detection, where we're building a time series model and identifying unusual events or unusual data in the time series model. The other one is data frame analysis, which is really more of a you know, creating your own models and using those models and how you can use those models for your own data. So go for those two parts, but really first I want to start with kind of the anomaly detection. This is something that the machine learning team at Elastic has been working on, you know, for 10 years now. It actually was a separate company that joined forces with Elastic about 4 years ago, and they really have been building kind of a time series model of your typical logs, metrics, event type data, maybe telemetry, and looking at that data to detect anomalies or outliers from a group. You know, if you have unusual users, unusual IP addresses, or rare events, and I'll show you some of that in the demo. Like if you have unique processes or users that are accessing your system, and you see that in the log data, we'll build visualizations and alerting around being able to identify what's normal and what's unusual. And we've built a sophisticated UI around being able to highlight and score that data so that it's easy for you to use and interpret. You don't have to be a data scientist to interpret the results from our data science algorithms. You just have to know, what being able to feed that data into Elastic Stack and use Kibana as visualization to see those anomalies. The anomalies also contain influencing information. So when you have an anomaly, you can get to the root cause much faster by seeing what else changed at that same time. What was the potential effect of the change in that data? As well, because it's a time series model, it's an unsupervised machine learning model for the time series model. We can actually forecast out that model into the future and say, where is this model going? If you're trying to forecast out how many users do I expect on my system, based on what I've seen historically, or how many systems, how many customers are accessing my site, based on my historic growth. So those are different ways of using kind of that time series model for many, many other use cases besides just anomalies. How does it work? It's really, we use historical data to learn the patterns and the periodicity in the data. You might have a daily periodicity, how your users maybe use your application, heavy in the morning, lighter in the afternoon, and might be a lunch break, maybe less at night. Well, our algorithms will figure out what is normal usage patterns and build kind of that light blue shaded area is our confidence band. How confident are we in that model that it will be in that range? And then we use that to predict the next data point. So if it stays within that band, it's within the normal model. If it goes outside that band, we give it a probability score of what was the likelihood of how far from the model it was. And that probability score, we look at all our historical data and give it a severity score of 0 to 100. So you can operationalize it and be able to create alerts or reports for the anomalies that you're most interested in. How unusual is that data compared to historically what we've seen in our model. So that is how we do it for the time series modeling. We've really used that anomaly detection time series model in a lot of our solutions UIs. Everything from looking at response time durations within the APM app. You can just turn on anomaly detection right in the APM for any of your services. In our logs app, we can categorize the log messages and look at am I getting a spike in a certain type of message? Am I getting a spike in the rate of log messages I'm seeing? Those are simple questions you can ask, but is really reliant on the time series modeling that we're doing in the system. You can turn that on very easily with just a single button within the logs app. Same type of thing, duration within uptime is already is an option. And then there's a number of anomaly detection jobs and configurations within the security app or the SIM app where you can turn on, like, if you're looking for rare processes, unusual or suspicious login activity, and dozens of others out-of-the-box configurations that are pertaining specifically to security type data. And I'll show you a little bit of that in the demo as well. So that's anomaly detection. And before we switch to kind of the data frame analysis, I want to give you a walkthrough of what the anomaly detection piece can do. So I'm going to just switch out of the presentation and show you. So I'm running my Elastic cluster on Elastic Cloud. So if you could just go to cloud.elastic.co, you can sign up for a free trial yourself. This is what, you know, the first page you'll see once you create your cluster. And if I just go into, you know, you'll see on the drop-down menu on the left-hand side here, there is an option for machine learning, which will take us to the machine learning interface. And I mentioned there's kind of that two groups, the anomaly detection, time series modeling, and kind of the data frame analytics where you're creating your own models. Your own models are in the analytics part here, but let's focus on the anomaly detection for now. We can see that we have groups of anomaly detection jobs looking at our the data that we've collected. We can manage these jobs, these kind of tasks to say, show me any unusual data out there. I've got a number of different data on a number of different data sources feeding into my cluster. You know, things that, you know, your common beats like audit beat or winlog beat or file beat. You know, you can use, I'm using the beats because they come with Elastic Common Schema, lets us highlight and introduce you to machine learning jobs without having to think about the jobs so much, more about kind of what data do I want to get in. You can get very, you can use this with your own data. It doesn't have to be a beat, any other way you're feeding data in. But if I just, you know, a simple, show you how to create something. So let's say I'm looking at my audit beat security data. I can bring up my audit beat index, and we have wizards to create your own. You know, if you're looking at trended data, you might look at single metric or multi-metric. If you're trying to figure out population job, compare a user to other users on the system, that would be like a population job. You can get into categorization of log messages and everything. There's a lot of wizards that you can walk through, and that we have all kinds of webinars on how to do that. But since I'm kind of focused on the SIM security aspect for this webinar, you can see how easy it is just to kind of look at, we have pre-configured jobs for you. If I wanted to look at suspicious network activity or suspicious authentication events, you know, I can just click on one of those and then just, let's give it a name, a prefix to our job. I'm just going to give it a quick one. I'll create that job. And now it's running in the background. I'm looking at my audit beat data. It's created the job, running it against my historical data, and will continue running against new data that comes in. If I view that, the results of that, we can see that it's, you know, it's collecting the data and going through all the data, looking for unusual events in my data. And now it's pretty much completed. We can see that we have a list of, you know, couple of different hosts that we're collecting audit beat data from. You know, I've got an anomaly here. Yeah, a very unusual spike in the data. We can look down at the list here. If we this unusual spike, we have a high number of suspicious logins. We typically have about 2.5 logins during you know, an interval, which is basically a 15-minute interval. But for this interval, we had 38 unusual authentication attempts. And they were all coming from this one source IP. So that's an unusual number of authentication attempts from one source IP. We can go in and investigate this source IP. You know, we have actions that we can drill down into. And that was an unusual spike. There are other ones in here. You know, for other IP addresses, this one actually had more login attempts, but it wasn't that as unusual. For that time period, we can drill down and look at the details of that IP address and what they were doing. So this is actually this drill down is taking us right into the SIM application, because remember, it was the SIM wizard that automatically created this audit beat event. We can see where was that IP address going, what was the destination IP, how many times were they trying to log in. We have a number of, what user was he trying to log in as, how many documents, how many events do we have basically of that user logging in. So it can drill you down into very detailed, but it's nice because you can get kind of that high level view of what is unusual in my data. Sometimes really hard to look at, to see unusual things when you're just looking at the raw logs or at a dashboard of events. This allows us to see kind of those spikes and changes in the data. You'll see that we can do that across many other types of data as well. I showed you kind of that audit beat. If I created a, something for my WinLog beat, same type of thing. We'll get a list of authentication or unusual processes and network activity. Really nice and easy wizards to get you started here. And here we have a list of 1, 2, 3, about 9 jobs around unusual Windows processes that we can go and create to get you started quickly. And these are templates. You can change these. You can learn from them, make your own templates, make your own machine learning jobs. But really nice, quick way to get started looking at security data within Elastic. The other that helps with the SIM map. You can also, like in our other areas of observability, we can actually I've got some on my other cluster here. I'm collecting data from my own local system, looking at system log data. I can look at the log rate. I've been collecting logs for the last week and see if there's an unusual spike in the number of logs, types of log data that I'm collecting. So my syslog logs, if I'm seeing spikes in that, I can see when that happens and maybe where it happened. And we mentioned the categorization. If I wanted to see what are the content of my logs, and am I seeing unusual content? I might have I'm getting a lot of these messages. Here I'll go to one class is undefined. I might want to look at one of these and see some examples of what those log messages look like. So you can drill down into those categories and see, when did I get a spike in that data? It gives me kind of, a nice spark line there of how often that category happens. And, I can just go ahead and drill into it. I mentioned we have this in the Logs app. In Uptime, it's very easy to look at the add anomaly detection for different configurations. So if I wanted to enable it for my Uptime, I can just enable it for a specific Uptime monitor in there, and I can see if I'm getting any anomalies within that data and zoom into it. And also in the SIM app, if you go down to SIM, you have that ability to add ML jobs right from within SIM and turn them on. I showed you how to create them from the machine learning interface and create machine. This would do the same thing. I just have to go ahead and turn those on and have that information then will display right in my SIM map. If I'm looking for anomalies, I might look at my anomalies for a specific application. So really easy to get started, quick way to use machine learning for anomaly detection. and a lot of workflows built throughout the user interface for for the data that you're collecting on. If I go back to presentation, we talk about anomaly detection as an unsupervised and pattern recognition machine learning job where you don't have to feed it. You don't have to say what is good or what is an anomaly or what is an anomaly. We'll figure that out. You just turn it on and tell it what data, what fields to look at, and even what indexes are interesting. Those, and it will identify the anomalies and score those anomalies for you. But there is a whole set of other use cases that are used in machine learning that we call supervised machine learning. And that's where we take a labeled data set and we use that to learn and to make predictions on. And that goes across many different types of categories of machine learning capabilities. And we're building a lot of this into Elastic as well. We have a model for understanding what language is a message coming from. So if you need to send that to the right language processor, we have customers using it for, identifying what fields are for fraud or user classification. There's a lot of things you can do, and a lot of reasons you'd want to create your own models. Some of those might be search use cases for relevance or recommendation ranking or that language detection. Some of them might be observability use cases, like what users or hosts are outliers. How do you classify alerts and say which alerts are more important? What customers are likely to churn? You might have multiple features or like fields that you want to use to identify a model for, to predict customer churn and identify which customers are at the most risk of churning. And then we have like a number of security use cases, and that's where I really want to focus on now is kind of, some of them might be a classification of your users, but one of a really good use case is around domain generated algorithms. And I'd like to pass it over to Camilla now to walk you through how you can use our supervised learning for domain generated algorithm classification.
Thanks very much, Tom. So hello, everyone. I'm Camilla. And just bear with me while I try to share my screen. So here we are. 1 second. All right, so I hope everyone can see the slides. If not, please do let us know in the chat box. So as mentioned, my name is Camilla, and I'm a machine learning engineer with the machine learning group at Elastic. And today I'm going to be taking you through a practical application of supervised learning. And what we're going to be doing today is training a classifier. So classification is a flavor or a kind of supervised learning. And we're going to be training a classifier to help us detect malicious domains generated by so-called domain generation algorithms. So first, I'm going to go over a few slides to introduce the problem that we're trying to solve and to give you some context, and then I'll show you how all of this fits together in the stack in a live demo. So first of all, what is a domain generation algorithm, and why would we be interested in detecting if there is some DGA activity on your network? So let's start by considering malware. Once malware has infected a target machine, it usually needs a way of communicating with a server that is controlled by the attacker. So this is a so-called command and control server, or a C2 server. Now, in order for this malware that's infected a machine to communicate with this command and control server, it needs to know the domain name or the IP address of this command and control server. Now, one way an attacker could encode this information in the malware binary is to simply hard code the domain name or the IP address. But this approach would make it really easy for the people trying to defend their network to thwart the efforts of the malware to communicate with the C2 server, because all one would have to do is to reverse engineer the malware, get the domain name or the IP address, and simply add it to a block list so the two would not be able to communicate anymore. So in order to subvert this defensive measure, the attacker adds a special algorithm to the malware binary. And the only function of this algorithm is to generate hundreds or maybe even thousands of random seeming domains. Now, this algorithm is what we call a domain generation algorithm, or a DGA. And now when the time comes for the malware to try and contact the C2 server, what the malware does is it cycles through each of the hundreds or thousands of domains generated by DGA, and it tries in turn to resolve the IP address of each to see which one of the domains has been registered by the attacker as the location of the C2 server. Now you can see that immediately this kind of approach creates problems for someone trying to defend their network, because not only do you have to deal with a high volume of data, DGAs can produce hundreds or even thousands of domains, and it would quickly become impossible for a security analyst, let's say, to manually verify each domain that's trying to contact an external server. And in addition to that, these domains are often random looking and don't necessarily follow a pattern. So it would also be impossible for a security analyst to use a kind of a rule-based approach to try and block these. So because we're dealing with high data and because rule-based approaches don't really work very well here, this makes it an ideal problem for machine learning to solve, because instead of trying to come up with rules or trying to do block lists, trying to keep up with all these domains, what we can do is we can train a supervised classification model to distinguish between malicious and benign domains. So let's take a look at how we can actually do this in practice. So in supervised learning, the key feature that you have to do is to supply a labeled data set. And this labeled data set is what the machine learning model is going to use to learn to distinguish between malicious and benign domains. So in our case, our data set would obviously include benign domains such as Google, YouTube, Instagram, and so forth, and then malicious domains. So these are samples obtained from malware, from different malware families, and so forth. Now, the next step that we have to perform is something called feature engineering. Although the Elastic Machine Learning product will do a lot of these kinds of feature selection things for the user under the hood, we still do need to tell the model which parts of these domains it should pay close attention to in order to be able to best distinguish between malicious and benign domains. Now, this is where we have to kind of look a little bit at the benign and malicious domains and try to develop an intuition of what are the exact parts of the domain that the model should be looking at closely. Now, if you look at these two boxes on the slide, the blue one, which represents the benign domains, and the red one, which represents the malicious domains, we tend to notice some patterns. So for example, the benign domains here in the blue box tend to be dictionary words or human pronounceable words, whereas the malicious domains in the red box tend to be these kinds of random looking garbled strings. Now, although this distinction isn't as clear-cut for some malware families, it does tend to apply to a large enough sample that it's good enough for us to use for this demo. So based on this observation that we've just made, our hypothesis would be that if we told the machine learning classifier to look at the frequencies of different strings and frequencies of different characters and substrings present in the two domains, it would soon learn to associate certain characters and substrings as more indicative of benign domains and certain characters and substrings as more indicative of malicious domains. So we can encode this intuition that we've just observed in something called n-grams, which is basically just substrings of various lengths. Unigrams are single characters, bigrams are substrings of length 2, and so forth. So through a bit of experimentation, because this process of feature engineering is always iterative. So you start with an idea, you train the model, you check its performance, and then you kind of go back to a drawing board and you iterate until you've found some features that give you good enough performance. So through a process of iteration, we found that breaking up a domain into unigrams, bigrams, and trigrams gives us a pretty good result, and is also fairly easy to achieve in the Elastic Stack using painless scripts. So this is what we ended up using for this use case. And here at the bottom of the slide, I've just illustrated what this feature engineering process would look like in practice. So here on the left, this is a malicious domain. And you can see that by expanding it into unigrams, bigrams, and trigrams, we basically simply break it up into substrings of different lengths. So now that we have our features, the next step would be to actually train the classification model. So I'm not going to dwell too much on this slide because I'm going to go through this in more depth when I actually show you the demo environment. But it's just good to note that this is what the wizard will look like. But as I said, I will go into more detail a bit later. So finally, let's return to our original goal. So we want to combine all of these components in the Elastic Stack and put together something that can detect malicious domains that might be active on your network. So a common way to ingest network activity into Elasticsearch is to use packetbeat. And so what the final goal of this demo would be is to build some kind of pipeline that can take your packetbeat data, that can use the model that we just trained to distinguish between malicious and benign domains, and then can examine each domain that's being ingested with your packetbeat data and enrich it with a classification, which will tell you whether or not this domain is likely to be malicious. So in order to put this all together, we will need several components. So first, of course, is packetbeat, which is the component that you will use to collect the data. But then we will also need to configure an ingest pipeline with several different kinds of processors that will do this job for us. So first, we will have some painless script processors that will extract the features that we need from the domains in the packetbeat data. Then we will need an inference processor. So this is a processor that can hold a trained machine learning model and then use it to enrich the document. And then also we will need some painless script processors to clean this up. You will see how this all fits together in the demo that I'm going to show you next. So let me just switch over to the demo environment here. All right, so we are in Discover. I'm also running on cloud on version 7.6.2, but you can also repeat these exact steps with a later version of Elastic. And so let's start at the beginning of this whole process, which is training the machine learning model to distinguish between malicious and benign domains. Now, as I mentioned before, in supervised machine learning, you need to supply a training data set that will teach your model which domains are benign and which domains are malicious. So this is what our raw data set looks like. So it's quite simple. We have a domain, and then we have a label, or a so-called dependent variable, which simply contains whether or not this domain is malicious. So as you can see, this is a benign domain. So the next step in training the model was to perform feature engineering. And we saw in the slides that kind of the best, or one of the best approaches for DGA detection is to break up the domain into unigrams, bigrams, and trigrams. So as I mentioned before, you can quite easily achieve this feature engineering within the Elastic Stack by using a painless script processor. So here in the dev console, I have a simple example of a painless script that will achieve this n-gram extraction for us. So we have a simple painless function, and we can pass in here into the function n. So this is the length of the substring. And then out will come the different substrings of a domain that we pass in. In order to get our raw data into the format that we need to train the model, we can use an ingest pipeline and re-index the raw data. So we will simply configure this ingest pipeline with script processors. And you can see here that I'm passing in the n-gram count. So this one will determine how long the n-gram is that's going to be extracted by the script. So here is 1, 2, and 3. because I want unigrams, bigrams, and trigrams. And then the final step will be to simply re-index the raw data and pass it through this n-gram expansion pipeline. And so what comes out is the data that we will need to train our model. And I just want to briefly show you what this n-gram expansion will look like. So as you can see, here is a domain, and it has been broken up into its component substrings. All right, so now we have our training data, we have our features, we can move on to the next part, which is training the model. So we're here in the data frame analytics UI, and I'm gonna briefly show you kind of how we create these jobs. So up here in the wizard, you can select the classification job. You can fill out some information about the job, such as the job ID. You can add a description here if you wish. You can select the source index and a destination index. And then this is the important bit, so the dependent variable. So this is the variable in your training data that will contain the ground truth labels. So in our case, this variable will be whether or not the domain in question is malicious. All right, so that's one important component. And the second important component is this idea of a training percent. So when we're doing supervised machine learning, we usually tend to split the training data into two parts. So we have what we call a training data set, and we have a testing data set. And we set this testing data set aside, and we don't use it to train the model. And then once we have trained the model, we pass the test data set through the model, and we check to see how well the trained model performed on the test data set, which it hasn't seen before. Now this performance on the test data set gives us what's known as a generalization error. And it's an important measure because it tells us how well the trained model will perform on data that it hasn't seen before. And it gives us an indication of how well the model will perform on packetbeat data once we'll actually deploy it in production. So it's quite hard to say, there is no hard and fast rule for what you should configure as a training percent. 80 could be good, 70 could be good. You have to give it a try, and you also have to kind of figure in the size of your data to properly configure this. Because this training process does take a few minutes, I'm not going to do it here. Instead, I already have a trained job, so I'm just going to show you the results UI and just briefly show you how you can evaluate your trained model. So here we have the data frame results UI, and this is for the data that I just showed you. So we're trying to train a model to distinguish between malicious and benign domains. Here at the top, we have a summary of the model's performance. This is known as a confusion matrix. And it shows us how many of the domains that were not malicious were predicted to be as not malicious, and how many that were actually malicious were discovered as malicious. So you can see that our model was able to, in 98% of the cases, to make a correct prediction. So this is quite a good performance, but you should note that we do have a false positive rate of 2% here. And although it doesn't look like a very high percentage, if you do have a high volume of DNS data, this can tend to mean that you could have a high number of false positive alerts. And I'm going to show you a bit later how you can use our unsupervised learning capabilities of anomaly detection as a sort of second order analytics on top of this to reduce the number of false positives. But basically at this stage now, we have our trained model, we have an idea of how the model will perform on our testing data set, which we can toggle from here, from this filter here. And so we kind of have all the components that we're going to need, and we can move on to the next stage, which is configuring the ingest pipeline that's going to be needed to enrich our packetbeat data. So just so we have an idea of where we're going, I'm going to switch over to Discover for a second, and I'm going to show you what packetbeat data looks like. just so you kind of have an idea of what the goal is. So if you remember from the slides, our goal is to have a packetbeat document ingested that's enriched with the machine learning model's prediction of whether or not the domain is malicious. So here in Discover, I have a sample packetbeat document that's recording a DNS request for this very strange looking domain. This seems to be very highly likely that this is some sort of DGA activity going on here. And you can see that if I scroll down, this packetbeat document has passed through an ingest pipeline, and it's passed through the trained machine learning model. And the machine learning model has taken this domain, it's broken it down into n-grams, and it's kind of decided that this domain is very likely to be malicious. So that's kind of the end goal where we're going with this whole demo. So next, I'm going to jump back into the dev console, and I'm going to show you some components that go into configuring this end-to-end pipeline. So first, of course, we need to get the trained machine learning model. So we already took a look at the results in the UI, but now that we've trained the model, we can also get it from the console. So we can go to ML/inference, and we can see some information of information about the model. The most important piece of data that you have to kind of note from this part is the model ID. You will need this to configure the inference processor a bit later. Now, the next part is, because we used n-gram extractions to train the model, we will also have to perform the same n-gram extraction on the domain that we get from packetbeat data. So this is a painless script that's very similar to the one I showed when I was re-indexing the raw data. And it simply gets the domain that the DNS resolution is being asked for, and it breaks it up into n-grams of various lengths. And it just does it on the specific packetbeat field. And now finally, we're moving on to putting this all together in the ingest pipeline, which will allow us to enrich the packetbeat data. So here in the dev console, I have the ingest pipeline configuration. Just like we had in the re-index pipeline, we have the 3 painless script processors here that are taking in the domain from the packetbeat data, extracting the n-grams, and then they're passing it to the inference processor right here. And as you can see, we've added the model ID here, which means that the inference processor is going to know to use this particular model for the incoming data. We have a few other pieces of configuration here. And then finally, at the end of this ingest pipeline, we have a set of other 3 painless script processors. And what these do is they basically reverse the action of the first 3. So in order to avoid cluttering your packetbeat index with all of these extra n-grams, which you might not necessarily need, of course, if you do want to keep them, you can just remove these processors from here. But for the sake of saving space, we're going to remove the n-grams. So this is basically what these 3 processors do. They just remove the n-grams. So all you have at the end of this process is this packetbeat document, which has the usual packetbeat fields that you're used to. And then it just has the extra enrichment fields that were added from the inference processor. So I'm going to switch over to the slides for a second, just for the end of the demo. As I mentioned, while we did see quite a good performance of the model, we did have a 2% false positive rate. So if you have a high volume of DNS data, this can mean that you will get a fair number of false positives. Now, the cool thing with this is that you can combine the unsupervised features of the Elastic Stack to kind of perform second order analysis with anomaly detection. And the first thing to note is that if you plot the labels assigned to your packetbeat data against time, what you will actually get is a time series, which is perfect because that means we can pass it into our anomaly detection job, and that will sort of help us to further enrich and make a better detector. So just finally here, before I wrap up, just to show you what a time series of predictions would look like in an actual network situation. So with DGAs, it's common that when a malware is trying to use a DGA to contact a command and control server, it will generate a kind of spike in DNS requests because it is obviously cycling through hundreds or maybe even thousands of domains in a very short span of time. So you will see these kinds of waves, and then in between of the peaks, you'll see this kind of subtle activity. So this is the background noise of false positives. So this is the thing that we're going to use anomaly detection to kind of get rid of. And even with just a simple job, which checks the counts of domains predicted as malicious, over time, you can kind of see that if we have an anomaly detection job just running on the results of the inference processor, we can see that it accurately picks out the kind of peaks in DGA detection and it alerts on those. But when we're just having this false positive background noise, we don't really get any alerts. So I don't have much time to go into detail about how this would work, but just to give you a flavor that you don't have to stop with inference and supervised learning. You can mix and match. You can combine it with the unsupervised capabilities of our stack to sort of further enrich your detection capabilities. So I think that's it for my part, and I'm going to pass it back to you, Tom.
Great. Well, that was the end of the presentation. We do want to take any questions that you have. So if you have questions, please feel free to add them to the chat. Jenny, do you see any questions yet?
I think you're muted, Jenny.
Yes, Silver, thank you. If you do have questions, please select all panelists and attendees so we can all see your questions.
Just to, I mean, some of the general questions, this will be recorded for those that have registered for it. You'll get the recording. The machine learning capabilities that you've seen today, both the anomaly detection and building your own models, require a platinum level or higher subscription to Elasticsearch. They're not in the free version. And we have done other webinars on supervised learning and constructing your data set in the last 6 months. So feel free to look on our website at the videos. There are several others around kind of machine learning and different machine learning use cases. If you want to drill into any, like specifically anomaly detection ones and the supervised learning ones. Let's see. So those are some of the typical questions. Are there any others, Jenny?
We do have a question coming in. How does the roadmap look like for AI ML for SIM?
We are continuing to add out-of-the-box configurations for many more data sources, and the SIM has added detection rules and ways of being able to alert on those. I can't really go into the SIMS roadmap myself. That would be for another session, but you could definitely reach out to your account manager or SA to get more detailed information on that.
All right. Thank you. I see there was a comment in the chat, and so this presentation is super informative. Thank you, Riley. All right, if there's no other questions, we're going to announce what's coming up for next month. This will be a customer interview, so it's going to be really, really interesting. If you would like to learn how to monitor and and prevent threats as employees transition from home to office. And just come join our next SLED virtual user group. It's going to be on July the 23rd and 2 p.m. Eastern Time. Thank you all very much.
Thanks everybody for joining today and for watching the recording.